Hi everyone, I'm Sachini Peoni Ekanayakar. I'm a PhD student at the Department of Electrical and Computer Engineering, University at Albany State University of New York. I'm working with Yasita Lienage and Dr. Daphne Zeiss from the same department. Our paper is on dynamic feature selection for classification in structured environments. Now let's get started. In many real-world application domains, example medical diagnosis, behavioral analysis, Bayesian networks represented by directed acyclic graphs are used to describe relationships between variables. However, such variables are not directly observable, but instead can be inferred through access to noisy but costly features. For example, affective state and personality traits of individual which are only observable through noisy GSR, ECG, and EEG sensor data and self-reported questionnaires are related and thus can be represented by a Bayesian network with two classification variables. Now I am going to briefly describe related work. The wide applicability of Bayesian networks in various domains has led to the design of various classifiers for such networks. However, such methods typically assume that the Bayesian network represents the relationship between a single classification variable and a set of noisy features, and thus the goal is to infer the value of such variable. On the other hand, prior work on Bayesian networks for supervised learning consider more than one classification variables. The relationship between are represented through a non-Bayesian network structure. The objective in this case is to infer the values of all classification variables in the network, exploiting their relationships. Still, such classification variables are assumed to be fully observable. Our prior work considers a single classification variable and dynamically selects a subset of the available features and reaches an appropriate classification decision during testing. In this paper, we propose a method to dynamically select features for classification of structured data instances, that is, data instances where relationship between classification variables are represented using a non-Bayesian network. Specifically, our proposed approach dynamically selects a subset of the available features and reaches an appropriate classification decision for each variable in the Bayesian network during testing. Classification decisions are propagated through the Bayesian network starting from the lowest degree nodes and used during the classification of the remaining variables. Now I am going to describe our problem. We consider non-Bayesian network structure G described by a directed acyclic graph. Here, X is the set of n nodes corresponding to n categorical variables in G. E is the set of directed edges that represents relationships between variables. A set F of features is available where fkxi denotes the kth feature associated with variable xi. EKI is the associated feature cost for each feature fkxi and CLXI represent the class value for each variable xi. Misclassification cost is MLMI, which represents the cost of selecting class CLXI, while the true class is CMXI. The problem is shown in a picture here as an example. The objective is to infer values of variables in X by balancing classification accuracy with the total cost of selected features. This is our optimization setup. Consider the pair of random variables Ri, Dri associated with class variable Xi. Random variable Ri represents the last feature selected from the ordered set of features associated with variable Xi. Random variable Dri represents the classification decision associated with variable Xi. Since Xi is a categorical variable, Xi belongs to one of ni possible classes. As a result, Dri takes values in the set as shown here. Our goal is to sequentially select the minimum number of Ri of features to reach a classification decision Dri by minimizing the cost function shown here. Here this probability represents the joint probability of selecting class CLXI while the true class is CMXI. The first expression denotes the total cost of evaluating Ri features in the sequential process, while the second expression penalizes the misclassification errors. To solve the optimization problem, first consider the posterior probability phi k vector as shown here. The probability phi km denotes the posterior probability of the mth class given the set of k features for variable xi. Based on this posterior probability and dynamic programming, we derive the optimum stopping strategy. The last stage is defined as the self function. This represents the optimum cost to go at last stage, which is equal to cost of stopping g phi k. In any intermediate stage, the optimum cost to go is defined as minimization of two functions, cost of stopping and cost of continuing. Here we define cost of stopping g phi k using misclassification cost defined as a matrix M and posterior probability phi k. Cost of continuing L tilde function is defined here. Finally, the optimum classification strategy DRI star is given by this equation. The proposed approach consists of a training and testing phase. During training, all possible posterior probability vectors phi k are computed by quantizing the interval belief space for each variable as described here. Then using that phi k vectors, stopping cost and continuing cost are numerically computed. This procedure is done for all variables in the Bayesian network. During testing, the numerical solutions determined during training are used to dynamically select features and reach a classification decision for each variable xi in the Bayesian network. Here, this figure shows a graphical representation of the proposed approach for an example Bayesian network G consisting of 4 binary random variables. Original Bayesian network and corresponding features are shown in this figure. A. First, the process begins by initializing the posterior probability for each variable xi. If the cost of continuing the feature selection process is less than the cost of reaching a classification decision, the first feature in the set f xi is selected and the posterior probability is updated. The process is repeated until either a subset of feature is selected or all of the variable features are reviewed. In either case, a classification decision is reached using updated posterior probability along with the optimum classification strategy. Starting with nodes of in degree 0 in the Bayesian network, proposed approach sequentially selects features and reaches the classification decision. For example, in figure B, we can see that x1 is an in degree 0 node and it is classified using 3 features. Next, considering the structure of the Bayesian network, proposed approach moves on to nodes with in degree greater than 0, for which classification decisions for their appearance have been reached. As illustrated in figure C, x1 is a parent for x2 or x3. Since x1 is already classified, x2 or x3 is classified next. Selected features at each round of the proposed method are highlighted. We can see that variable x2 and x3 are classified using 5 and 2 features respectively. This process is repeated until all variables in the Bayesian network have been assigned a classification decision. To test the performance of our proposed approach, we use two datasets, a synthetic dataset and a real-world dataset as described here. To estimate this conditional probability, maximum likelihood estimator was used. Further, we consider that the misclassification cost MLMI equal to 1 when L equal M and otherwise 0. Further, evaluating cost EKI for variable I is considered as E for K and I. Fivefold cross-validation results are reported. As baselines, we use two standard classifiers, one offline feature selection method and our own prior work. Now let's look at the results. This graph illustrates the trade-off between accuracy and feature cost for different cost values under the assumption that features incur the same cost. The accuracy for each variable as well as the average accuracy of variables G1, G2 and G3 are reported. As expected, using different feature costs leads to different accuracy levels, while acquiring more features typically leads to better accuracy as long as such features are informative. The frequency of features selected during testing demonstrates the importance of different features on classification decision. For example, in this figure, features school and failures are most often selected to classify all variables. Intuitively, students, school and number of past class failures have high impact on students' grades compared to other features. Further, in order to compare the performance, we used accuracy, training, testing time, and average number of features. We observed that both the proposed approach and IDANA use less than the 30 available features, contrary to logistic regression and IBase. Lasso, on the other hand, even though it performs feature selection offline, still uses most of the available features. With respect to accuracy, we observe that the proposed method achieves the best accuracy, even with respect to IDANA. This is expected since the proposed method takes advantages of the relationships between variables in the Bayesian network. With respect to time, the proposed method runs much faster than IDANA, but slower than the baselines. Putting our findings into perspective, the proposed approach is able to achieve best accuracy by selecting the most informative or low-cost features while significantly decreasing the time requirements of IDANA. In summary, we introduce a dynamic feature selection method for classification of structured data instances. And also, the performance of proposed method is validated on synthetic and real-world datasets. Finally, as future directions, we plan to extend this framework to account for correlated feature spaces. Thank you so much for listening to my presentation. If you have any questions, feel free to email me. Thank you.